Hi everybody, before I want to start, I want to ask you a question. What happened to the kid here? And his parents did not neglect him. What's actually happened that the kid went down the slider and attract electrostatic charge, but only the hair of the kid sensitive to this effect. The reason is because the ratio between area to volume. And if you're going to check it, it depends on the inverse proportionality of the thickness of the hair. And something similar happened in the aerosol world. Aerosol also very sensitive to electrostatic effect, and this is well known in the industry. So how electrostatic relate to our world, the respiratory world? So when an aerosol get out of inhaler, neutralized inhaler, it accumulate charge and only then get deposit within our body. And this is a well-known phenomena. Different kind of inhalers accumulate different amount of charge on their aerosols. So, hi everybody, I'm Ron from the Technion, and I want to share with you my findings regarding electrostatic in the lungs, especially in the deep pulmonary lungs. So, how does electrostatic affect the deposition? So, if we consider the lungs to all its scales, when an aerosol gets in proximity to the tissue, it's gonna make a dielectric effect and suddenly gonna be attracted to it by electrostatic forces. And I want you to notice to a key parameter, the distance from the tissue, which is inversely proportional to the distance. So the electrostatic effect should be really strong in the small compartment of the lungs when we are really close to the tissue compared to the upper airway, which is really big. So in general, our finding in the research that I'm going to share with you, I saw in the acinar region completely dominant of charge for these sizes, and I did a separation between septal deposition rather than into the cavity deposition, and also in the bronchioles I see a dominant effect of electrostatic. So let's dive into the scary equation, the particle dynamics, and when we add the electrostatic, the equation becomes nonlinear, not easy to solve, and in this case we have two different approaches. One is simulations, and the other one is non-dimensional analysis. I'm sure most of you familiar with the non-dimensional analysis, but if not, I'm going to simplify it. Instead of solving the equation, we're going to present big numbers, numbers that are going to present the phenomena. If one of the numbers completely bigger than the other numbers, it means that this phenomena is dominant. And for the lungs, we have the Stokes number, how hard it is for the particle to follow the different route of the lungs. We have the inverse Paclet number, which means diffusion is governed the equation. We have H, which is gravitational sedimentation, heavy particles. And last but not least, we have INC, short for induced charge. And all of these numbers depend on the specific length of the compartment of the lung and the velocity. And I want to remind you, the lung is a really hard problem to solve because it's a multi-scale problem. The length scale always changing, and the velocity reduced as we get deep into the lungs. So the electrostatic effect been investigated in the past, but in vitro models only in the upper airway. As I told you before, I think it's misleading, because in the deep lungs, perhaps we have an opportunity to understand. So I plot here my non-dimensional analysis. So the horizontal is the charge from different inhalers, and the vertical line is different sizes. Of course, I see three dominant numbers for the big particles, gravitation, no surprise there. For the small particle, diffusion, but most of the scenarios of aerosols being governed in the deep acinar region by electrostatic effects. A mild amount of charge, a little bit more than those of a nebulizer, would be controlled by electrostatic effect. So, of course, we also have the region of superposition when two effects take place, or even three. So let's see the deep region of the lungs, how we can investigate them. So we have four main challenges in order to develop an in vitro model that's going to tell us how electrostatic affect the lung. The first challenge is to have the real anatomical scale of the acinar region, hundreds of microns. We want respiratory flow, a real flow velocity, creeping flow. We want electrical conductivity similar to those in the lungs, and we want it to be transparent so we can see inside what's going on. So I built the model by glass. I took a glass with a dicer machine. I cut trenches within the glass, and eventually I would have in my region of interest 6 different cavities with the anatomically physiological sizes. Remember, it's a 2D cavity, okay? And to take care of the electricity, I use atomic layer deposition to make it covered by ITO layer, a conductive material which is also transparent. And then I need to take care of the velocity, the profile, and I use a microchannel that I designed. This is our region of interest, and I'm gonna do a cross-section to explain to you the methods how I build it. So I took my diced glass and 3D printed cast top of a PDMS. I supply air to the model, and the air split into two different flows. To the pipe, bleeding, then I get rid of all the high velocity that don't depict the scenario in the asinar, and the small reciprocatory flow to the cavities controlled by a syringe pump. And then I check with simulation that the flow indeed simulate the lung. We have separated flow within the cavity. My exposure setup was designed to have to use polystyrene latex because I know the charge they're gonna produce in this method. And as a control group, I have the neutralizer to compare what happened when the same particle would be neutralized, grounded my model, and saw it under inverted microscope. So here you can see a single alveolus. Each sphere presents a particle that's being deposited in the septa or in the cavity. And here you can see all the 6 cavities that I have. And I want you to notice that the z-axis presents the height of the particle with the color code. And you immediately see a lot of red particles. I'm gonna come back to this point later. So let's make it more numeric, more numbers. So if I'm gonna see the deposition fraction, how 100 particles would deposit in the model. So for the heavy particles, like raindrops, they're gonna fill the cavities. But when the particle get charged, I see that most of the particle being attracted to the septa. So charge increased septal deposition. For the diffusion particles, we have the opposite scenario. We see that small particles deposit a lot of the septa and slightly more in the cavities when they're exposed to charge effect. So I want to apologize for some limitation that I have to my model. My model septa is pretty big, 4 times more than the real thing. So to compensate for that and to the fact that I have only 6 alveoli and not 300 millions, I calculated the area of my cavity and correct my result by the area. I normalize the result, and here you can see a really important graph. So here you have the ratio between concentration of particle on the septa versus the alveoli for 3 different sizes. So you can see that in the septa, for the neutralized case, we have 10 times more particle on the septa. But when get charged, 50 times more, almost. And for the half micron, we see almost double the effect. And for the small particle governed by diffusion, we see inverse effect. The charge helped the particle get into the cavity. And I want to emphasize something really important that I hear in this conference all the time, that size plays a significant role. I want to see what's happened when the same particles get charged. We have order of magnitude difference and the same result when the particles were charged. So I really want us to emphasize the importance of the electrostatic charge we have on our inhalers. So we cover the upper airway, I covered the deep asinar region, and the question remains, what's happened on the way? The small bronchioles.